Tom's just going to make a quick announcement.
Okay, sure.
Yeah, I guess I already clapped. Whenever you're ready.
Okay, good. So, okay, so before we go to the penultimate talk, there is a very, very last, completely unofficial CASI event this evening that some of the organizers are looking forward to. There is a somewhat dystopian space which has been converted into a food truck parking lot and a bar. It's called the Rayback Collective. Rayback, okay, R-A-Y-B-A-C-K. It's on 28th Street up at around Valmont. We are going to gather there. I'll probably get there 5:30 or 6 or something like that. Okay. You'll see all of Boulder, enjoying Friday afternoon. Hopefully it won't be raining. What else should I say about that?
I'm happy to lead your group up for people interested
Yeah,
to walk over.
it's a little bit of a walk.
It's a walk, yeah. So I'm happy.
Yeah, but on the other hand, they all have, they can all get an Uber if they have to.
Yeah, for those who are walking, fine. I don't know, we can whatever. 4:45.
Anyhow, this is absolutely unofficial. Okay, do not bring your name tag. But you can bring your T-shirt. That will impress the crowd.
One more very unofficial thing before I turn it over to Jure. So thank you everyone for being into the puzzle piece thing, which I know is healthy, but I really appreciate meeting everybody through the contest. I think 6 of you are still not collecting puzzle pieces, but only 6, and 1 organizer is not collecting puzzle pieces. Sorry, 1 speaker is not collecting puzzle pieces.
Why are you pointing at Ken?
So anyway, so if you're one of those 6 and you are persuaded by the rest of your peers having puzzle pieces, please come and introduce yourself and anytime between now and then.
All right. So the last lecture of this series will have, so I'm super ambitious, which means there's no way I can do everything I wanted to do. But I'll write on the board what is in the nodes. So first, dark sectors, which basically will be axion like particles. But unlike Ken, I will switch on flavor violating couplings. So this will be very important. So if they have flavor violating couplings, the phenomenology changes, and we'll see why and how. So I think this we will cover. Then the next one is Higgs as a probe of flavor. So that's hopefully we'll go over this. And then the last one was standard model puzzle. So standard model flavor puzzle. So that's, as if you remember, if this is the masses of different standard model fermions, that would be the top quark. And then somewhere down here is the electron. And in between, we have many other fermions. And then down here are the neutrinos, where we only have an upper bound, which is milli-electron volts. The question is, why this structure? Why the CK mixing PMNS structure? So there's model building. If you think this is something that needs explaining, as Matthew said in his first lecture, it's somewhat akin to the elements, the periodic table. Maybe there's some dynamical explanation. So this I will put in parentheses. Yeah, it's very unlikely I'll get that far. But it's in the notes, and I'm happy to just talk to you after the lecture if you want to ask questions. All right, so I said dark sector, axion-like particles when we switch on flavor violation. There are other fields that you can do the same thing, like a scalar with a flavor violation or a gauge boson. But the nice thing about the axion is that there's a scale associated. So if I write down let's say a QCD axion, or an axion-like particle Lagrangian, so it's an ARP. So this Lagrangian for an ARP is a kinetic term, there's a mass term, and then there will be gauge interactions with the ARP, and then the interactions with the fermions. So I wrote explicitly here the mass term. So if the mass is a free parameter, this is what I mean by an ARP. So if it's a free parameter, anything goes. That's an ARP. A QCD axion, the mass is given by, so it's inversely proportional to this UV scale where the Peche-Quinn symmetry was broken. I think we heard a little bit how this arises, and this is the QCD contribution that then gives the mass to the axion. So this would be a QCD axion. All right. Not sure if I gave the numbers, but basically for the scales that we'll be interested in, 10 to the 10 GeV or so, this is well below an electron volt. It's more like 10 to the minus 6 electron volts. And if you are doing decay, if you're looking at the decay of a meson, this is basically massless. No? So the QCD axion in these experiments will look like a massless thing. It has a very, very small mass. An ARP, however, not. No, it can have even a GeV scale mass. All right. Okay, so the couplings to the gauge bosons. All right. If I need, so well, maybe I should write them out. So basically, there will go as A over FA, and then there will be for the QCD, so the GG tilde, you saw it already. They would come from fermions. They can be heavy, where you would have either a gluon. It will generate a diagram like this, but if I have, instead of a gluon, I have a WI, there will be also some normalization, A over F, W mu nu I, W mu nu I tilde, and also for the hypercharge. Not writing the normalizations, it's also important. So these are dimension 5 couplings, and basically I wrote anything that you can write that has axion and a gauge field. And we'll do the same thing for the fermions. We'll be completely agnostic. So if I take an ARP fermion, effective Lagrangian, the only thing that we will use is that this is a PNGB, so there will be a derivative coupling. So PNGB or F. It's a factor of 2, right? And then couplings to fermions, where I allow for a completely arbitrary structure. 5 FJ, right? So you can have both axial and vector currents. I allow here. It's just fantastic.
Can you have explicit CP violation by having A coupled to just GG and not GG tilde?
Yeah. So the question was whether I can have explicit CP violation where I have GG tilde and GG. In principle, yes, like from low energy perspective, I should write down everything. The fact that this is an axion is exactly this, that I want this to come from the anomaly. Therefore, I only keep those guys. The story here is different because, I mean, yes, you're right, the CP, if I have these guys non-zero, CP is violated, but it comes from a different sector. It will come from the Yukawa interactions, and all I need is this PQ symmetry to be different, the charges for the PQ symmetry to be different for different generations, right? So it's kind of morally they come from a different, they are different, no, these terms. But you're right. If I was completely agnostic, I omitted some terms, yes.
Should the gamma mu be outside of parentheses?
There's a gamma mu here. So the observation was that I either should have moved gamma mu out, but I instead brought it there. Yeah. Okay. So and this F's now is up, down, quarks or the leptons, which means right now this I wrote already in the broken phase. Like while this Lagrangian I wrote in an unbroken phase, so that's why I wrote them into different blackboards. They're not really written at the same scale, but it's I could have just have a left-handed fields, break it down. There will be relations between the CV and CA couplings for up and down quarks. Right, so there's some relation that comes from the fact that this is all embedded in SU2 invariant theory. They're not. You can do the counting of the parameters, and you find that there are 36 parameters in total. So it's quite a lot of parameters. So now how do we make a sense of this phenomenologically? And there's actually a nice kind of discrete choice that you can make. And so the choice that you can make, and this is phenomenologically very important, is, so first choice you could say, are there flavor violating couplings in the UV? All right, so that's the first. Let's say that this orthogonal couplings, they're order 1. The other option was that no, they're not. However, in the standard model, I do have flavor violation in the quark sector. So if you include these corrections, you will generate flavor violating couplings just from the fact that there is a flavor violation in the standard model. They will be proportional to the CKMs and therefore suppressed. So this is the first choice. Are there flavor violating couplings which are large? The other one is, you say they're not, but you will still generate them. The other choice that you need to make is this really a QCD axion? So massless on collider scales. From here, this will mean that it's invisible. It will escape the detector. Or it's an ALP. And in this case, it can decay inside detectors. Right. All right. Maybe I'll just move over. All right. So I'll go through an example for a kaon decay. So we'll pick a kaon decays. And let's see what happens when you go over these discrete choices. So the production here will come from the S to D A transition. Something like this. I have S, D, and it's split off an axion. If I have a valence U bar antiquark, this means that I have a transition K minus to, let's see, most people are still looking there. There are questions? No. All right, so from K minus to, so from K minus to pi minus, the relevant couplings are going to be these two. So let's say, let me call option 1, CDS-V at the UV scale is order 1. And then option 2 is CDS-V is generated from loops. Loops. All right, what kind of loops? So I can have an S that converts to a D through a W, and then from the diagonal coupling to the top, or C or U, I could have a contribution like this. This will be suppressed by VTS, VTD. Sorry, it's getting small, but it's VTS, VTD CKM elements. Maybe I can cheat. All right, VTS. VTD. So this is of order lambda, and this one. Let me move the C here. Right, so if I have a C, this will be VCS, VCD. So different suppression. I'm doing the same thing. So VCS, VCD. This is 1 lambda. Okay. I can do the same thing for a U. So this is okay. All right. So from this, like if you were to pick which one is the largest, all right. But what if I dial all the quark masses to 0? So if I dial all the quark masses to 0, then all these flavor relations should vanish. No? So this thing should also be proportional to the masses floating around. So therefore, the top Yukawa is much bigger than the up Yukawa. This guy will win once we write down everything. And then the final one is, if I go at this Lagrangian, there is also this piece here, right? So I can split off an ARP from the W leg. So once the dust settles, and I write the, I will just exchange this. Go. All right, so now let me write the value for CDSV at the scale of 2GV will be, so it will be the value at the UV, and then plus I sum over these fermions, T and C. I can draw up U, you'll see in a second. This is the suppression from the masses, and I made them dimensionless already. V, F, S. And then, of course, the coupling to that particular fermion, right? So if I couple to the top, this coupling also appears. And then a log of the ratio of the two squares. UV over this small, let me call it mu c. So I have to write, this is mu c, right? Minus some loop factor. All right, I need at least something to denote, so I'll call this piece N2 with some normalization, and it's normalized such that N2 in a model that you would write down, this would be some order one number. All right. Numerically, it's maybe more important. So this piece is going to be, it comes out to be 10 to the minus 6, comes from the loop factors and the CKMs, and then 2 plus I, CTTA times this log, and the UV mu c, plus 0.08 CCCA, again this log, lambda UV over mu c. You already see the trend, no? So the up quark, most likely I can completely forget unless I have a very particular flavor structure in the UV. And then order 10 to the minus 3 times this factor N2. All right. So there's a hierarchy of contributions. If you are in a theory where all the couplings that are naively order 1, like if I can switch on all the couplings and they're all of the same size, there's no flavor structure, then CTTA is 1-ish, CC is also 1-ish, N2 is also of order 1, then the flavor violating coupling at the low energy is completely dominated by the coupling to the top, right? And you see that now the only question is flavor violation in the UV, no? Is this something that is much bigger than 10 to the minus 6? No? Naively, with like my choices were, it's either or the 1 or 0. If it is 0, then it comes from here. If it is or the 1, you can just completely forget about these corrections, no? Right? So that's this choice, this discrete choice that you can make, and this will govern a lot of the phenomenology. All right, so that was about the production. Now about the decay. Yes, oh.
This process,
There's
do you
more
care about
questions.
CA at the scale you see, or is this just CV?
So the question was why I have A and V appearing here. No?
Do we also need CA at the scale 2GV?
Ah, yes, now I understand. So the question was, do I need CA at scale 2GV? I'm interested in a particular decay k to pi minus A, which where only the CV piece contributes. If I instead looked at a different decay, then both CV and CA would contribute also for hyperons. So it's really, I simplified our life by looking at the simplest case, and then in this simplest case, it's only the CV that contributes. There was one more question? Yeah. So the question was, what is the lambda UV? And this, I will say this is the same as F. And it will be, if you want numbers, 10 to the 10 GeV in one case, and much smaller in the second. So the second will be more like TV-ish, 10 TV or so. No? Yes, one more.
Do we need to worry about this logarithm being large now?
Yes. In principle, the question was about the size of this log. So this is 10 to the minus 6. Log of 10 to the 10 over 2 is 20. So yes, instead of 10 to the minus 6, maybe it's 10 to the minus 5. But the message is exactly the same. 10 to the minus 6 is so small that you really now have a discrete choice. No? Either you have some theory where, if you think of a theorist, no? The theory is either my PQ is agnostic about flavor, or I have different charges for different generations. If there are different charges for different generations, this will end up to be most likely something which is order 1-ish, no? Or very heuristic. Other questions? Okay. All right, so that was about the production. I said now about the decay. So the decay is, of course, very important because it will govern phenomenology. I picked kaons because I have a much simpler time describing all possible decays. So in this case, I have either A goes to 2 photons, goes to E plus E minus, or goes to mu plus mu minus. In principle, I could also worry at the very end of the pi plus pi minus. But this it covers all the possible modes that are kinematically allowed, or there was the option that A is just escapes the detector. All right, so the decay width for the decay to 2 photons will be, so where would this come from? No? So they would come from the fact that you couple, the very least now you couple to quarks. You have contributions like this. You can also have contributions that are coming from the, and then there's the UV plus the coupling to photons from the UV. All this we can lump to C some parameter. We call it C gamma effective. And I think, I'm not sure I wrote the Lagrangian down. But it's normalized such that this would be order 1 in a typical theory, So let's do the exercise for this. In that case, the C tau A will be order 10 to the 7 meters times FA over TV squared. I should just, it's too bad. On the iPad, you just do this, and then you move it somewhere else. So let me delete. And then I said C gamma effective. And this was all normalized such that you have an order 1 thing. F over, I think I put TV, yeah, squared. And then A. So, and then 1 over this C gamma effective squared. So the scaling of MA cubed is easy to understand. The couplings to photons go as 1 over F, because all the couplings to fermions, they go F. And all the couplings to the gauge bosons were also 1 over F. So this needs to be now proportional to 1 over F squared, right? The amplitude squared. To have a dimension for decay width, I need to have MA cubed. Right, so that makes it the right dimensions. I do an inverse and I get the C tau A, that's the decay length. And you see it's huge. Even if I have TV, so very low F. So unless MA is at 100 MeV or so, well, if it's at 100 MeV, then you will start seeing this in the detector. If it is very light, especially if it's a QCD axion, which is below an electron volt, forget it. No, it will never decay through to photons inside the detector. So how about these guys? So here, C tau A will be 1.9. It's really not important. So roughly meters. F over TV squared. 10 MeV over MA times the coupling of squared. So instead of 10 to the 7, we have meters. Where is this coming from? It's coming from the fact that this is a 3-level coupling to electrons, while the photons, everything is generated at 1 loop. 1 loop factor is 1 over 16 pi squared. You square it, and you get this factor of 10 to the 7, 10 to the 6. All right. I had to put 10 MeV here, so something much bigger than an MeV, so that you can comfortably decay to electrons. So that's more representative. For the muons, the only difference is that now I have to change. This should be cubed. is it not cubed? All right. So the only difference is now that this will be heavier. It has to be heavy enough that you can decay to muons, right? So let's put 100 MeV Ma cubed, coupling to now muons, and again still F over TeV squared. So now I will get this will be 10 to the minus 6 meters, right? Doesn't quite work. It should be 10 to the minus 3. I don't know, something's wrong in my notes, but because I put 300. But anyway, so the height of the decays is the following. So if you decay to the photons, it's very likely that this will just be an invisible guy unless you are in a 100 MeV case. Then if you couple to electrons, you're decaying on the collider scales inside, but it could be either something which is instantaneous, or it could decay reasonably far away from the production. If you're decaying to muons, it's instantaneous. So that's the signatures. You can have displaced vertices, but not for the muons. Okay. Most importantly, out of all this numerology is no matter what the couplings of the QCD axion are, in the detector at colliders, it will appear as an invisible signature. It does not decay inside the collider. So that's this difference. QCD axion will appear as an invisible signature. ARPs, it's more complicated. Can decay, maybe they don't decay. No, it depends. All right. So now let's look at some what the experimental landscape is. So okay. So I had these two options. It was option 1. This is big in the UV. I have big flavor violation in the UV. So how does the measurement look like? So option 1. In the UV, if this is order 1, that you probe for all the ARP masses so you will probe F, which is slightly bigger than 10 to the 11 GeV, for MA, which is basically 0 to 250 MeV. Remember, this is from the K to pi A decay. And let's assume that it doesn't decay into anything. So if it's an invisible signature, it's a huge scarce. Now to have a point of reference, the cooling bounds. So I know Caitlin told us that we're supposed to put this into, but if I don't say these words, nobody will know what I'm talking about. So the extra, so if you have other mechanisms to take the energy out of the stars, aka axions, these bounds will live at about 10 to the 9 GV or so. Oh, so less. Let me see. Yeah. It's important on which side you are. Yeah. So you see, this is about 2 orders of magnitude more sensitive. Why we're laughing with gain is because there's also a lower bound where the axions get trapped inside the stars. So this is more sensitive than the astrophysical bounds. However, they come with from different couplings. This is directly probing the flavor violating coupling. This thing is probing the flavor diagonal couplings, either couplings to electrons or GG tilde, basically neutrons, protons. So these are flavor diagonal. If all the couplings are order 1, you can compare the 2 bounds. If they are not, if the flavor diagonal couplings are order 1, but these are suppressed, then of course you have to readjust. The other point of reference that you want is, so this 10 to the 11 GeV is much bigger than the bounds on new physics that came from K-bar mixing, for instance. So K-bar mixing. So this came as lambda new physics. They were squared operators. And this lambda new physics, if you remember, anybody remembers what the scale was? All right. Yeah, we need units also. Okay, yeah, so there is noise from the audience, so 10 to the 4, so TV. So that I translate, let's say, to GeVs now, so 10 to the 7. So 10 to the 11 is much, much bigger than the 10 to the 7 GeV. So why are these invisible decays more sensitive to the UV scale than this type of observables? You gain because what we're really looking for is a branching ratio of K minus 2 pi minus A. So this will be the decay width of K minus 2 pi A divided by the standard model decay width of the K minus, right? So the standard model decay width of the K minus will come from transitions like this, no? So I have, this will of course be converted to it's really K to pi. But the important thing is that I have an off-shell W, right? So this decay width will be proportional to 1 over m W to the 4th power. I need to make it dimensionful, so it will be also proportional to mk to the 5th power. It's a huge suppression, no? Kaons are relatively long-lived. And you gain, so I'm measuring this new physics decay width compared to something which is already very small in the standard model. And this is, let's say, you find that the bound on this is, I don't know, smaller than 10 to the minus 7, no? Something like this. So that's the experimental thing, no? Is how many kaons I'm able to see. But I gain because I'm measuring against a small standard model rate. No? While in the KK bar mix, I need to measure the oscillations. So it's a completely different measurement. So parametrically you gain because I have this small decay width. Right? So maybe I should write it. So parametrically, it's maybe good to see. So parametrically, Where was it? Ah. So this will go as mw squared or mkf squared. Okay, so in other words, no, it's important that this comes from dimension 5 operators, because I have 1 power of f in the amplitude for the new physics. The mw squared comes from the standard model decay width. So I put mk here to make this dimensionless. And you see that parametrically you gain, no? If I had a decay which was mediated by heavy new physics, so I have S, let's say S, D, something like this, I don't know, some Z prime, the amplitude will go as lambda new physics squared, right? And then I divide by the standard model width. This is already dimensionless, branching ratio for this new physics. And there's no search like this. This is completely just to get the parametrics right. You see there's no parametric gain, no? So heavy new physics, you really count on the fact that you have to do some precision probes. You have to find observables that are not of this type. No, this is stupid. No, you will never be able to compete with the standard model. Here you gain, because it's light in physics coupled through dimension 5. All right, enough about this. So option 2. Any questions before I go to option 2? All right, so option 2 is everything comes from the loops. So this is heavily suppressed. This flavor violation is heavily suppressed. And then all these searches where, I can have now k minus goes to pi minus a, and this guy goes to 2 photons, e plus e minus, gamma gamma. They all become relevant, and they are important in different regions. So it's a colorful plot that you end up with, but important. And it also matters what you now assume for the particular couplings. Do you couple to gluons? Does this ARP couple to up or down quarks? Does it couple to a W? These bounds will change in details, but the main message will remain. So typically you bound scales which are of this type. Okay. All right. So I think I'll switch to the Higgs. So there's more to be said now. These are, of course, not the only probes. You need to look at the probes where you directly produce, for instance, an ARP from an E plus E minus collision, or from the beam dumps. In the beam dumps, the ARPs are coming from the decays of this type. So secretly, you are probing this. However, how does the beam dump look like? No, you have, let's say, a proton. You dump this beam onto a target, and then all sorts of stuff comes out. You're interested in these exotic decays, this type, B minus to pi minus A, etc. Let me pick this line. And then, so there's dirt, shielding, and then you put a detector at the end. And if A decays to, let's say, an E plus E minus, you can observe it. So that's the setup for the beam dump. Which is, you see that you will only see the lifetimes that are long enough such that the axion does not decay inside this, I don't know, could be 100 meters of material. So it's very different. However, the underlying physics is the same. You will produce them from these flavor violating decays. Right? So that's why I said in the first day that secretly you are doing flavor physics if you're doing light in physics. And the reason why this dominates is, of course, the same, is that you have relatively big branching ratios because you always compare to the standard model, which is suppressed. Directly bramming off axions is much harder. Okay, so that's the, okay. So I switch to the Higgs. Is there questions over this part? All right. So Higgs is a probe of flavor. So the idea here is very simple. No? So the Higgs field in the standard model has a dual role. All right, so first of all, so it breaks electric symmetry. And it gives, from here, inevitably you'll get masses for the WZ gauge bosons. However, it also, there are Yukawa couplings. So it's the minimal thing, no? You just write, you use Higgs for both giving the masses to the W and the Z and the fermions. So standard model fermions, right, through Yukawas. So the having Higgs giving, and this gives masses to all the fermions. No? So all the, in the standard model, all the fermions, even the electron with a, only a half an MeV mass, gets the mass from the Higgs. Now for the top, there's not much you can do. No? The bulk of the top mass should come from this electric symmetry breaking, because otherwise I have to have an extra large source of electric symmetry breaking. For the rest, it's more fair game, no? So especially for the electron, if I have just a tiny bit of an additional electric symmetry breaking, I can fully give the complete mass to the electron without ever talking to the Higgs, right? So if that's behind, that the masses of the standard model fermions are coming from some other sector, how would I know? Well, I look at the decays of the Higgs, and I try to see whether it matches the standard model or not. So the question is, how well have we tested this structure, this minimal structure? Now here, it helps that we're kind of a decade into this program, so there is no sign of new physics at the LHC, which minimal explanation would be just that the new physics is heavy enough that we didn't see the signal. So that's what we'll do. We'll assume heavy physics, right? Integrate out, and we'll get SMEFT. I should say, or so in that case, so SMEFT, you assume that the Higgs that we see is part of electric doublet, and there's no other source of electric symmetry breaking. So there will be the dimension 4 Yukawa coupling, but then from this heavy new physics, I can start writing higher dimensional operators. Both of these will contribute to the fermion masses once the Higgs obtains a wave. No? So this will have one wave. This thing will have V cubed sitting. Both of them will contribute to the masses. Lambda ij and lambda ij prime are not aligned. So if there are two different matrices, then once you diagonalize, you will have the fermion masses, but the Higgs will have a contribution which will be off diagonal. So the Yukawa couplings will have off diagonal pieces. Let's see. Maybe I should do this. All right. So once I have electric symmetry breaking, that will enter here. It will enter as right? So that's the Higgs field plus the electric wave. Now I can write the masses will be V over square root of 2 plus minus lambda ij squared V cubed times f j. However, for the Higgs, I have lambda ij over square root. And then from here, I pick up 3 times h v squared plus minus. That's the Higgs. So that's the Lagrangian. No? So this is, you diagonalize this first part, you get the fermion masses, but you see that the two matrices come with different combinations. There's lambdas. There is. No? With two different combinations, there's a factor of 3, an all-important factor of 3. So in general, this linear combination is not diagonal in the same basis as this linear combination. Right? Any questions? I'm scared about just a few nodes. So the outcome is, no, if I have extra new physics with flavor violation, like here, general flavor structure, I will end up with a Lagrangian at after electric symmetry breaking that will look something like this, no? I will have for the couplings to the of the Higgs to the fermions. So we'll have diagonal couplings, where conventionally we'll normalize this to the standard model, H, and then also the off diagonal, F prime, we can have L F prime F right, Higgs plus H bar C. And then I can also put in gamma 5 here, and I could have an I sitting here. So plus CP violating piece, which looks like something like this. I'll just talk about this part for now. All right, so there's the flavor diagonal pieces that can differ from the standard model prediction, but you can also have flavor of diagonal contributions. All right, so what are the standard model predictions are that I have this kappa F is equal to 1. That's standard model. And kappa F prime is 0. That's the standard model prediction. So now you can ask, experimentally, you can ask several questions. So how well is this obeyed? So the first question you can ask are so if I look at the Yukawa couplings of the Higgs, are they proportional to the masses? Right? Or rather, so do the Yukawas grow when you have bigger masses? Then this factor of proportionality is this the standard model one? So this would have been my IJ in the standard model. So is this square root of 2 over V? So is this, are they all on the same line? So if you plot, maybe you've seen these plots. So if you pick mass of the fermion versus the coupling, they should all lie on the same line. Here would be top, and then a B, and then what's measured is also a muon. And then people also plot the W and the Z, which are somewhere here. So they all lie on the diagonal. There's some error bars, but seems to work. Then all right. So the next question that you can ask are these Yukawas, do they have flavor violating couplings? And the final one is right, so are they imaginary part of these Yukawas? Are they 0? Or is there CP violation in couplings of the Higgs? All right, so the proportionality and factor of proportionality from here, you can see that it's relatively, so it's well tested for, I forgot the tau. Let's see if here we go. Tau. So it's well tested for the third generation. From the second generation fermions, we only have muon. Charm, there's an upper bound that is relatively interesting, but still well above the standard model. For the first generation, the bounds are super weak, no? The flavor violating Higgs couplings, on the other hand, are, so the story there is the following, so let's look at these flavor violating Higgs couplings. So if we were to find the couplings that are off diagonal, of course that would immediately imply new physics, because in the standard model, this is 0 up to one loop corrections, which is well below the present sensitivity. And for charge leptons, so if you have Higgs to, let's say, tau mu, tau e, mu e, in principle, you can access this directly. Right? So you produce the Higgs, and then you look for the decay of Higgs to tau e, mu e, because you are able to measure in the detector whether or not you have a muon or an electron. If you're interested in the Higgs decay to, let's say, B bar S, this is extremely hard, no? Right? So this we only have sensitivity indirectly from, let's say, B sub S mixing. Right? So indirect. In fact, for the Higgs to mu e, the indirect bounds are also very severe. So you can imagine that you would generate mu to e at the loop level, where you have a muon here. If I have this flavor violating coupling, this will induce mu to E gamma, which is the very important constraint. For instance, it constrains branching ratio of Higgs to mu e to be below 10 to the minus 8 if there are no other contributions that cancel this one. Right? So that's a severe bound. Means that you have to view 10 to the 8 Higgses is something which is a tall order, right? So 10 to the minus 8 would be very hard to get to these very small branching ratios. So unless there are cancellations in the UV, Higgs to mu e is something that is constrained indirectly severely enough that there's the likelihood of having these decays at the LHC is very small. How about these guys? So what is the scale that is being probed? Right, so the branching ratios that are being probed correspond to the Yukawa or E tau that are less than about 10 to the minus 3. Right, so that's an order of magnitude smaller than the bottom Yukawa, right? And this corresponds to, it comes from higher dimensional operator. So what is the value of lambda? If I assume that these small lambda are order 1, the capital lambda, so the scale of new physics this corresponds to, is going to be tau, or E tau, is about 5 TeV or so. Okay? So 5 TeV is something that is not very far from the mass scales that you probe directly at the LHC. No? So in order to see an effect in this Higgs to tau mu decays, if you have an effect there, you will also have the states that are producing this. It's very likely that you will be able to produce them on shell. All right. Any questions? All right. So the CP violating couplings also fall into kind of two types. The ones that you can probe at the LHC would be, for instance, the coupling to tau. The ones that are indirectly well constrained are the ones, for instance, for the electron, they would come from the EDM. So there's indirect and direct constraints, similar as for the flavor violating ones. All right. Okay, so I have glorious 4 minutes left. So I can say just a few words about the standard model flavor puzzle. So that's the parenthesis. Okay, so the solutions, what are the ideas that people are thinking of? And I'll be super brief. So the ideas fall under, there could be a symmetry reason. They go under horizontal. Horizontal just means that you go from one generation to a second generation because the quarks in these plots, so this would be 1, 2, third generation, and these are the gauge bosons. So you remember these PR posters where you have a Higgs standard model and it's horizontal. It's very stupid, so it's a horizontal symmetry. So it just means that you distinguish between different columns. All right, so what this will buy you is that if you charge the standard model fields differently, let's say if I have an right-handed up quark and the first generation left-handed doublet, if they carry different charges under, and the Higgs, let's say, is uncharged, then I cannot write a Yukawa like this. No? So this is forbidden. So that would explain why these are small numbers. Like this is small. It's forbidden. But if you give it more structure, for instance, if you have vector-like fermions with spontaneously broken symmetry, you can write now a chain where you couple the right-handed to the left-handed. This is supposed to be a propagator of heavy fermions. Each of them has are charged under this flavor symmetry such that this Yukawa with the extra scalar is invariant. So is this one, so psi prime. So by having a series of states, you can now connect the two standard model fields. Right? So that's the idea, is that they're not directly, you cannot write a dimension 4 operator, but you can write a higher dimensional operator, which would have some suppression. So that's a VEV. If this is 0.2, then you can build a hierarchy out of this. So there's a small hierarchy, is the VEV over the mass. The rest is extra dimensions. So you can put a Higgs on the brane. The standard model fermions propagate between the two branes in the fifth dimension. And the hierarchy comes from small overlaps or big overlaps on the UV brane, on the IR brane. So that's maybe something called partial compositeness. It's very related. You talk to the Higgs is in the strongly coupled sector, and there the hierarchy comes from very large anomalous dimensions, so very decently large range of anomalous dimensions where you couple the standard model fermions to this sector. And then what became relatively popular in the last 2 years is something called flavor deconstruction. So here the idea is that the gate symmetries, our standard model gate symmetries, are part of a bigger gauge group, and this gauge group knows about the generation. So you would charge the third generation differently than the first two. So this would be. And Nathaniel is guilty of doing this a decade ago. I think it sat dormant for a while, and now people are picking up these ideas. So you can build a hierarchy out of these behavior sequential breakings into the standard model. That's kind of a very bird's view of these model building attempts. I'm happy to talk about this more, but I think it's good to be aware that there are ideas out there. All right, thank you for your attention.